In this video, we will learn to design a hydraulic cylinder from scratch. First, we will cover the basic concept of each hydraulic seals, including piston seal, rod seal, buffer seal, wiper seal, and guide rings, their roles and the selection. Next, we will learn how to properly arrange these seals within a hydraulic cylinder, focusing on the groove design and appropriate tolerancing. Additionally, we will examine the tolerancing and surface finish of the cylinder bore, piston rod, and the seal groups. Most importantly, we will learn how to determine the clearance between the piston housing and the cylinder bore, known as extrusion gap, which is a critical parameter for every seal's life. So, by the end of this video, you will master the optimal design of any hydraulic cylinder. Now, this video is going to be too much detailed. So first let me quickly make you familiar with every components of a hydraulic cylinder and how they work together. So in a hydraulic cylinder, the first obvious component we have is a cylindrical barrel, a well-finished surface hollow steel tube, mostly made of mild steel, and it's bolted with the head. We can call it front head and rear head. However, these heads can be also tightened with tie rods, something like this. Or the head can be threaded inside the tube as well, depending on the design of a hydraulic cylinder. And then we have a piston inside the cylinder to do the reciprocating motion using the oil pressure. And it's connected with a rod. We call it piston rod. Now, this is a dual acting cylinder. So we have two oil ports at the both ends. So when we need to extend the piston rod, we supply the oil from rear side, from this side, through a directional control valve, which pushes the piston forward, and we direct the oil on the other side of piston to the tank through the front port. And when we need to retract the cylinder, we direct the oil supply from the front port and direct the rear port to the tank, oil tank, so cylinder can retract, right? Now, in a single acting cylinder that we mostly use only in vertical application for heavy lifting, there is only one oil port at the rear side. So to lift the weight, to extend the piston rod, we supply oil from the rear port of the cylinder, and the cylinder extend, lift the weight. And when we need to retract the cylinder, we direct the same oil port to the tank using a directional control valve, and the cylinder retract due to gravitational load of the weight over the piston rod. Now, the key difference in designing of a single acting and double acting hydraulic cylinder is in single acting cylinder, the piston has to seal the oil pressure only from one side, from the oil port side. But in a dual acting cylinder, the piston has to seal the oil from the both side, right? And not only at piston, we also have to seal the oil pressure in a front head of the cylinder, between the piston rod and the front head. Otherwise, oil will leak through the head. And now let's understand the hydraulic seals. So the seals on the piston, we call it piston seal. And the seal for the piston rod in a front head of cylinder is called rod seal. These seals are called dynamic seals because these seals between components in relative motion. In a hydraulic cylinder, the rod sealing system seals the dynamic reciprocating motion between the piston rod and the head, while the piston seals the dynamic reciprocating motion between the piston and the cylinder bore. Now, apart from these two main seals, we have also two more dynamic seals in a hydraulic cylinder, which are wiper seal and buffer seal. The wiper seal prevents environmental dust and contamination from entering into cylinder. And a buffer seal is used for dealing with high pressure peaks to reduce the high shock of pressure and allow a gradual change in pressure to prevent the main seal, the rod seal, from leak. We will discuss all these seals, their design and installation in much more detail later in this video. Now, apart from all these dynamic seals, we also need static seals at all the fixed connection. The most common static seals between the piston housing and the piston rod, and between the head of the cylinder and the cylinder bore tube. In a hydraulic cylinder, we generally use O-ring as a static seals, but a static seals can be a gasket or other sealing elements also. But in a hydraulic cylinder, we mostly prefer O-rings as a static seal. Now, we have to also understand the main role, the function of a hydraulic seals, whether a piston seal or rod seal, is seal the oil pressure and do not guide the piston motion. So, to properly guide the reciprocating motion of piston and the piston rod and to prevent metal-to-metal contact between cylinder components, we need guide rings. One is piston guide rings, which is guiding the piston inside the cylindrical barrel. And one is the rod guide rings, which guides the piston rod in a front head. So this was an overview of hydraulic cylinder components, the seals and the guide rings. And now let's start the detailed designing of hydraulic cylinder with an example. So in previous video, the complete guide to hydraulic cylinder sizing calculation, we calculated the component sizes for a hydraulic cylinder with a 20-ton capacity and a working pressure of 100 bar. You can find the video link in description. So the calculated sizes are bore diameter, the piston diameter 180 mm, rod diameter 80 mm with connection thread size M64 into 3, required stroke length 300 mm, cylinder wall thickness 12 mm, head thickness 32 mm, and the number of screws is 8 and the screw size is M16 into 2. So let's start with piston design. So here I have created a cylindrical block of mild steel, a piston housing block with nominal diameter of 180 mm, the bore size. We will define the exact tolerance after selecting the seals and the guide rings. As it depends on the seal's maximum gap, E gap. We will understand this later in this video. And the piston housing width can be determined by a formula involving radial load and the number of guide rings. I will leave this formula in video description. However, as a thumb rule, the piston housing width should be 1.5 to 2 times the piston diameter. Therefore, I have considered 200 mm. Now, the cylindrical barrel. So here I have roughly designed a cylinder with welded flange of calculated thickness 32 mm on the both sides for mounting of cylinder heads. The nominal internal diameter of cylinder is 180 mm and the wall thickness is 12 mm as per the calculation. Now, the hydraulic cylinder bore diameter tolerance should be under H9 feet. So for 180 mm, the upper limit 0.1 mm and lower limit is 0. And the cylinder length will be determined after adding the cylinder heads. And now let's add the piston rod of diameter 80 mm as per the calculation with a connection thread size of M64 into 3 and a flat key cut for tightening into the piston housing. Now, maintaining concentricity between piston housing outer diameter and the piston rod is crucial. So to achieve this, we will guide the rod within the piston by adding a guiding step. Considering a 70 mm guiding diameter, and to fix the rod into the cylinder, we can use a threaded step and a nut using the same connection thread M64 into 3. Now, here we need to add the O-rings to prevent the leakage through inside the piston housing. So let's select an O-ring for 70 mm diameter. Now for a O-ring, the piston housing holes H9 fit is required, and the recommended groove diameter over the rod, piston rod, is 60.3 mm with an H11 fit tolerance, and the groove length of 7.5 mm with tolerance of plus 0.2 mm, and the corner radius is 1 mm. And now we will add the rear and front cylinder heads with 8 bolts of M16 size as per the calculation. And to maintain the concentricity, we need to guide the step of heads within the cylinder bore and add the O-rings for sealing. Now, to prevent the nut from hitting the rear head, a proper spacing should be provided, something like this. And now we can add the oil ports on both heads, something like this, with an additional step to allow the oil to initially fill in a large area, in a circular area, to generate initial force, to initially give a push to the piston. Now, for our high-speed cylinders, we provide oil cushioning on both sides, on both heads, which we will discuss in a separate video. Now, we have to also understand that when a hydraulic cylinder operates, a high pressure applies over hydraulic seals. So, a hydraulic seals run over the cylinder bore under high pressure at high speed. Therefore, a rough surface finish can easily degrade the life of seals. And this is same applies for piston rod as well, for the rod sealing. So the cylinder bore surface finish should be RZ 0.4 to 2 micron, and this can be achieved by using readily available horn tube or by roller burnishing method inside the cylinder. And the surface finish over piston rod should be 0.4 to 2 micron, and it should be induction case hardened. The hardness should be greater than 50 HRC, and the hardening depth to be 1.2 to 2.5 mm, and it should be chrome plated of thickness 20 to 30 micron. So this is a basic layout of a hydraulic cylinder, and we will adjust the component length and sizes as we add the seals and their groove. So first we need to choose the right piston seal, and the seal selections depends on two main factors: the seal profile and the seal material. So there are basically three profile options for a piston seal. One is U-cap profile seal, made of single material, mostly polyurethane, and these seals can operate at pressure up to 200 to 350 bar, and the allowable piston speed with the seals is up to 1 meter per second. For more detail, refer to manufacturer catalog. And the key characteristics of this seal design is that it seals the hydraulic pressure only from one side, from U side. When hydraulic oil applies pressure, these seals expand radially and creating a tighter seal against the piston groove and the cylinder barrel. Therefore, for a single acting cylinder where the oil is need to be sealed from only one side, the U-cap seal is good choice. However, in a dual acting cylinder, we need to seal the oil pressure from the both sides. So this can be achieved by using two numbers of U-cap seal in back-to-back arrangement, something like this. We can also use the same U-cap profile seal as a rod seal, as the oil pressure is also from only one side. This is why this seal is very popular. Now, if a single seal is desired for the piston in a dual acting application, then we can use dual acting hydraulic seal, also known as composite seal or sleeper seal. Now, there are various seals profile in this category, depending on pressure handling capacity, speed, and lifespan. The core design principle of these seals involves two main elements: a base ring or energizer, typically made of nitrile rubber, which keep pressing outer ring radially, and the outer ring is called as slide ring, which runs in a hydraulic cylinder bore and provides sealing. These slide seals are generally made of polyurethane or PTFE. PTFE material seals offer very low friction, resulting in longer lifespan as compared to polyurethane seals. Dual acting seals can handle pressure up to 300-400 bar, depending on manufacturer profile and material. These specifications can be found in any manufacturer catalog. Now, for extreme working conditions, these seals is integrated with anti-extrusion rings, capable for handling up to 690 bar. Now, the third option we have is using O-rings with the backup rings for a working pressure below 100 bar. Now, you might wondering what is the backup ring and why do we use it? So when a seal faces high pressure, the seal's material is forced into the clearance between the piston and the cylinder bore. This process is called seal extrusion, which can permanently damage the seals or reduce its sealing capacity. And the dimension of this clearance gap is referred as extrusion gap or E gap or maximum allowable gap. So the clearance between the piston and the cylinder bore should not be excessive. The maximum allowable clearance gap depends on the seal profile, the hardness of seal material, working temperature, and working pressure. And we can find the maximum allowable gap, E gap, in a seal data sheet. For example, SKF U-cap piston seal UNP 180, 150, 19.5 at 80 degrees centigrade and a working pressure of 160 bar, the maximum allowable E gap is 0.6 mm. But at 350 bar, it's only 0.2 mm. Now, let's say if we want to use these seals at 350 bar or above, we should have to maintain this 0.2 mm clearance, 0.1 mm on a top, 0.1 mm on the bottom of the piston housing. However, this is the maximum clearance, meaning when the piston diameter is at its minimum size and the bore diameter is at its maximum size. Now, this is not difficult requirement for shorter stroke like 300 mm in our case, but for a longer stroke, let's say 200 mm, it would be difficult to maintain. So in some cases, if we cannot ensure the maximum E gap during manufacturing, or if maintaining such a small clearance would be in result of high manufacturing cost, we need alternative solution. So in such cases, we can operate on a large clearance and use a backup rings with main seals. Backup rings are just like a washer. It's made of hard plastic materials such as rigid thermoplastic thermosets and their composites, which resist the seals to extrusion in a large clearance. So therefore, when we use the nitrile O-ring, they are softer as a piston seal or a rod seal, always required backup rings. Now, as the given working pressure in our case is 100 bar, so I would prefer to avoid using O-rings as a piston seals. Instead, we can select either two U-cap design seals or a dual acting seal. So let's select a U-cap seal as it's readily available and cost effective. And here I'm referring to SKF hydraulic seals, specifically the UNP profile, which can handle up to 350 bar, well suitable for our working pressure 100 bar. And the working temperature range is -35 to 100 bar, which is adequate for our application. So for a 180 mm diameter, this is the model number of the seal. And here is the detailed data sheet including group dimension, tolerance, and the maximum E gap. They are available online by searching on a model number. You can also download the CAD model from the same source. Now, the primary function of a seal is to create a barrier for oil pressure, not to guide the piston within the cylinder bore. So to guide the piston smoothly within the bore, we need guide rings. So the guide rings are made of harder material, such as harder plastic, like polyamide or PTFE for low friction, or fabric reinforced composites. These materials have a higher degree of elastic deformation, providing a large contact area and better utilization of the guide width against the bending moment due to radial load on the piston and rod as compared to metallic bushings. So usually we use plastic materials as a guide rings. And mostly we use 2 guide rings on a piston at the both ends to minimize the radial movement during the load and the pressure changes. Now, these seals are typically split for easy installation and allow better lubrication. Some guide rings are designed to operate dynamically on either their outer side or inner side surface, and therefore that can be used as a piston or a rod application. For example, SKF's WAT series guide rings. Some are designed to operate dynamically only on outer surface, such as SKF PGR series, which is called as piston guide rings. Others are designed to operate dynamically only on their inner surface, such as SKF's RGR series, the rod guide rings. So here let's choose a piston ring from PGR series. For a bore diameter of 180 mm, we will select a ring with 40 mm width, and the full datasheet including groove detail and the tolerancing is available. Now I have a question for you. As we have 2 piston seals and the 2 piston guide rings, so in which arrangement you would like to install these seals and the piston guide rings? 1. Install the seals at the both ends and place the guide rings in middle, or placing the both guide rings at the ends and the seals in between in back-to-back arrangement, or alternating 1 seal and 1 guide rings. Please let me know your preference in a comment, but here I will choose to place the guide rings at the both ends, which will provide the maximum support against bending moment and the buckling load. And the seals will be placed in between, ensuring the rings are always lubricated, which is not possible if the guide rings are placed between the seals. So here I have created the groove for the both rings and the seals according to recommendation in their datasheet. And on end steps, I have maintained retainer height of 2 mm, 1 mm on each side. So the step diameter is 178 mm, 180-2. And in middle step, I have maintained an E gap of 0.6 mm. As our working pressure is less than 160 bar, 0.3 mm on each side. Therefore, the step diameter would be 179.4 mm, 180 minus 0.6 mm. So this is the minimum size, or LMC, least material condition size, and we will maintain this size in manufacturing drawing, considering as a bore diameter tolerance. So let's perform a short tolerance analysis. So first, the cylinder bore diameter tolerance should be H9 as per the seal recommendation. So for 180 mm diameter, the upper limit will be 0.1 and the lower limit is at 0. This means at LMC, the cylinder bore maximum diameter could be 180.1 mm, 180 plus 0.1. And as we have to maintain a maximum clearance of 0.6 mm, so 180.1 minus 0.6, 179.5 mm. Therefore, we can define the piston E-gap step tolerance as a 180 mm nominal size with lower limit 0.5 mm and upper limit as 0. So even if cylinder bore diameter is manufactured at LMC 180.1 mm and the piston diameter is manufactured at LMC 179.5 mm, the maximum possible clearance would be only 0.6 mm. And if the both are manufactured at MMC, maximum material condition, then the smallest bore size will be 180 mm and the piston maximum diameter will be 180 mm. So there will be no interference. Now, if you are wondering why I have not maintained this E-gap on the other side also, on the sides also, so it is not required actually because the pressure is applied from this side. So the seal extrusion will be only on this side. Now, to keep the oil pressure inside the cylinder, we need seals to prevent the leak between the rod and the head, front head. And as the pressure is applied only from one side, from this side, we mostly use U-cap profile design seal. Now, the U-cap profile design can be single or double lip profile, typically made of polyurethane. And there are also other profile variations, such as these are used for low temperature conditions. So you can explore the other seals profile based on your specific requirement. So for this cylinder, let's select a basic single lips profile S1S, which can seal up to 400 bar at handling the speed of 1 meter per second, well suitable for our application. So for an 80 mm rod diameter, which should be in F8 or H9 fit, the full technical details including groove dimension and tolerancing are available. And here we need to maintain an E-gap of 0.6 mm. Now first, the rod diameter tolerance should be H8 as per the seal recommendation. 0.043 mm and the lower limit is 0.106 mm. And to maintain a maximum clearance of 0.6 mm between the heads and the rod diameter, we will consider least material condition of the shaft. So the shaft diameter would be 80 minus 0.106 mm, 79.894 mm. Therefore, the head bore diameter maximum size would be 79.894 plus a 0.6, 80.494 mm. Now, we can define the tolerance over the head bore as 80 mm with a lower tolerance, with a lower limit of 0 and upper limit of 0.494 or 0.5. And now we need to add the guide rings for the piston rod. So let's select the one from RGR series, rod guide rings. For an 80 mm diameter, we will select this one, RGR 808650 PF with 50 mm width, as I am using only one guide rings. And we can make the grooves inside the head according to the given groove details, something like this. Now at the end of front head, we must use a wiper seal because a hydraulic cylinder operates in various application and environmental condition, including exposed to dust, contamination, outside weather condition. So to prevent this contamination from entering the cylinder assembly, wiper seals, also known as scrapers or dust seal, are fitted on the external side of the cylinder head. The design of a wiper seal is something like this with a single and double lip options. There also comes with metallic cap and can be installed in a press fit or using a snap ring or something like this. As we are designing for indoor factory application, the drawing application, it's a cleaner environment. So let's select the basic one, the MCW profile, MCW 8097 ECQ, and we can install it as per the given groove detail, something like this. Now, in a hydraulic cylinder, an abrupt pressure peaks can be occurs due to external force acting on the piston rod or initiated by the fluid inside the cylinder. And these pressure peaks can far exceed the system operating pressure, which can cause the main rod seal to leak. So in such cases, we use a buffer seal before the main rod seal. So what buffer seal does is not fully seal the pressure, but it's reduce the peak intensity of pressure, acting as an intermediate seals before the main seal. So in heavy duty application at high temperature and pressure, a buffer seal in combination with rod seal provides an effective sealing system for cylinder. These seals are usually made of lubricene, which is softer than polyurethane, or PTFE with a neutral energizer. In our case, the buffer seal is not actually required, but just for understanding purpose, let's select a basic profile, S9B 8095.1 into 6.3, and make the groove as per the recommendation. So this is a typical sealing arrangement for a piston rod. First, we have guiding rings to guide the piston rod, and then the buffer seal to reduce the pressure peaks, high pressure peaks, followed by the rod seal to completely seal the oil pressure, and finally the wiper seal to prevent the dust and contamination from entering the cylinder. Now, if you are designing hydraulic cylinders for other well-known applications, you can use the recommended arrangement provided by OEM seal manufacturers. For example, the Parker has defined the template for many applications. For example, excavator, wheel loaders, and bulldozer, forklift cylinders. And they also specify the seals profile, which is very useful for the seal selection. So this is it for this video. In upcoming videos, we will learn to make a manufacturing drawings of every components of hydraulic cylinder using the proper GDN tape. But before that, let's first understand the hydraulic power pack and its calculations. So next video should be on your screen, or you can check the video description. And thank you so much for watching this video.